Okay, hello everybody. In this module, we're going to be looking at the root locus. And since we studied the root locus in linear control, we're going to be just reviewing the root locus. We're just going to be doing an example and, just refreshing on plotting the root locus. As you know, the root locus, we use it to study the pole locations as a function of the gain of the system. So if I have a system, what happens if I vary that gain? Where are all the poles or the possible location of the poles of the system? The root locus gives me a graph of where all the possible locations of the poles as we vary the gain k of the system. Now the rules for plotting the root locus is in the z-plane is similar to that in the w-plane, in the s-plane. Now given a root locus, we can calculate the value of k for which the poles cross the unit circle, and therefore that will enable me to know the value of k that will result in a stable system or unstable system. We can calculate the value, we can also find the value k to achieve a certain pole location, assuming that pole is on the root locus. And we can predict the effect of adding additional controller poles or zeros on the system response. Okay. So if we were to look at this example, if we consider a discrete time system as an example for plotting the root locus, in this example we have a system that have a zero and two poles. We're going to use the Jury test to determine the range of k for which the system is stable. We're going to sketch the root locus, and usually we sketch the root locus for k that is between 0 and infinity. For a positive k, we're going to determine the gain k to obtain a desired set of poles on the root locus. Okay, so looking at this system, we're going to calculate the closed loop transfer function. This is the output y of z here. And if I calculate, since everything is in the z domain, I can just calculate y of z over r of z is going to be g of z, the forward path, over 1 plus g of z. And if I plug in for the forward path transfer function, I'm going to get the transfer function y of z over r of z, k multiplied by z plus 0.8 divided by z squared plus k minus 1.6 multiplied by z plus 0.8 plus 0.8k plus 0.6. So therefore, the denominator, if I take the denominator of the closed loop system and equate it to 0, that will give me the characteristic equation. So therefore, the characteristic equation for this system is going to be 1 multiplied by z squared plus k minus 1.6 plus 0.8 plus 0.8k plus 0.6 equal to 0. Since we're going to use the Jury test to determine the stability, this is a0, this constant. The coefficient of z is a1, the coefficient of z squared is a2. Now, since this is a second order system, we need to have q of 1 greater than 0, negative 1 squared, and this 2 comes from the order of the polynomial since it's a second order. And then we want a0, the magnitude of a0 to be less than a2. So if we plug in the value for q of 1, we're going to get 1 plus k minus 1.6 plus 0.8 plus 0.6, which is going to equal to 1.8 multiplied by k. We want this to be greater than 0, therefore k has to be greater than 0. We want negative 1 squared, q of negative 1 greater than 0. If we plug in negative 1, we're going to have 1 minus k plus 1.6 plus 0.8k plus 0.6. And this is going to give me, we want 0.2k to be less than 3.2, which means we want k to be less than 16. The third condition, we want the magnitude of, or the absolute value of a0 to be less than a2. So therefore we want 0.8k plus 0.6 to be less than 1, which means we want 0.8k to be less than 0.4, which means k has to be less than 1/2. Taking all these three conditions, k has to meet all these three conditions. Therefore, k has to be between 0 and 1/2. If we meet k less than 1/2, we would meet also the second condition. So therefore, the range for k for which the system is stable is between 0 and 1/2. Okay. Of course, when k is equal to 0, the open loop system has a pole on the unit circle at z equal to 1, and so it is not bounded input, bounded output stable. Since it's on the unit circle, it's going to be marginally stable. When k is equal to 1/2, the root locus crosses the unit circle, and it will become also unstable. And we'll see that when we plot the root locus. Okay. Now, if I look at the characteristic equation, d1 plus k multiplied by g of z, we have two branches since we have two poles, since the system is the second order. Now, as we know from linear control, the root locus starts at the open loop poles, which in this case z equal to 1 and z equal to 0.6, and it will end at the zeros, the open loop zeros, and the finite zeros and the infinite zeros. So in this case, the root locus will terminate at the finite loop 0 at z equal to negative 0.8, and the second branch will terminate at an open loop 0 that is at infinity. Since we have two poles, we're going to have two branches. The two branches are going to start at the pole locations, and they're going to end. If there is a finite 0, in this case we have a finite 0, which is the negative 0.8, one of the branches is going to end at it. The other branch is going to end at infinity, since there are no finite zeros. Okay. Also, we know that on the real axis, the root locus lies to the left of an odd number of poles and zeros. So therefore, if I were to plot the open loop poles and zeros, I have a pole at 1, we have 1 at 0.6, and we have a 0 at negative 0.8. The branches on the real axis that belong to the root locus are going to be to the left of an odd number of poles and zeros. So this green one is a branch that is on the root locus, and then the other one is going to be to the left of the negative 0.8. Both of these in green are on the root locus, and both of them are such that they are to the left of an odd number of poles and zeros. In this case, the one on the left, to the left of negative 0.8, there are 3 poles and zeros to the right of it. The other branch here, there is 1 pole to the right of it. So therefore, the root locus on the real axis is going to be to the left of an odd number of poles and zeros. Now, depending on the root locus we're plotting, there are different tools that we use to calculate information that will help us plot the root locus. One of them is to calculate the breakaway and break-in point. And to calculate the breakaway and break-in point, we take negative 1 over g of z, we take the derivative of that, we equate it with 0. And then that will give me on the real axis where the breakaway and break-in point are. So if I take the derivative of negative 1 over g of z, the derivative of z minus 1, z minus 0.6 over z plus 0.8, and calculate the derivative, equate it with 0, I'm going to get z1 that is equal to 0.785, and another z2 that is equal to negative 2.38. Now what we do, if you remember, we come to the root locus. If they are in a valid region of the root locus, then they're going to be a breakaway break-in point. If the value that I calculated here is such that it does not belong to the root locus, then we can ignore it. In this case, we have 0.78, which is going to be somewhere here. So therefore, it is part of this branch, and negative 2.38, which is going to be somewhere here. So both of these belong to a valid branch of the root locus. Both of them are going to be either a breakaway or a break-in point. How do we know whether it is a breakaway or break-in point from the values we calculated? We know that the root locus starts at the poles. So the root locus starts at the poles, and then as the gain increases, this is how it will behave. if we start here at 1 and negatives at 1 and 0.6, and then as the gain increases, we are moving, they're going to move closer to each other. Eventually, as the gain increases, we're going to have two poles at this location, and then they're going to start diverging and going out. So therefore, this tells me that this location, the 0.78, is breakaway point. Now, since this is a breakaway point, the other point is going to be a break-in point. The two branches are going to come in together, and as the gain continues to increase, as it goes to infinity, one of the branches is going to end at this 0, the other branch is going to end at a 0 at infinity, negative infinity. Okay. Now also, we can use the Jury stability test that we got to determine the location at which the root locus is going to cross the unit circle. Now remember, this is a discrete time system, so the stability is determined by crossing the unit circle. Unlike the continuous time system where we cross the j omega axis, here we cross the unit circle. So therefore, we know that when k is equal to 1/2, when k is greater than 1/2, the system is going to become unstable. So therefore, we can calculate the roots when k is equal to 1/2. So if I plug in k equal to 1/2 in the characteristic equation, I'm going to get the following roots. So these two roots are when k is equal to 1/2, and therefore I can come here and mark these two locations. Now this has a magnitude of 1, so it is, as we expect, is going to be on the unit circle, therefore it has a magnitude of 1. So this is one location, this is the other location. So what this tells me is that at k equal to 1/2, the root locus is going to be crossing the unit circle. So again, we're starting, the root locus is going to start at 0.6 at 1. As we increase k, they're going to come closer to each other here. As we keep increasing k, we're going to have these two branches, that one going to go up, one is going to go down. When k is equal to 1/2, I'm going to cross the unit circle. I'm going to cross the unit circle here, and as k keep going, I'm going to become unstable because my poles are going to be on this graph that I have here that are outside the unit circle. Remember, for the system to be stable, the poles have to be inside the unit circle. Okay, so this continues the poles are going to continue to go around this circle that I plotted outside the unit circle. This one here, this is the unit circle. And eventually, they're going to come back here. One is going to go to the 0, and one is going to go to the infinity. Now you can see also, one thing just to point out, even though here, as we increase k, we're going to eventually, one of the poles is going to become inside the unit circle. So somebody might think, okay, so there must be another limit on k. When I exceed it, I'm going to be inside the unit circle. But the fact that when these branches come here, one of them is going to go this way, the other one is going this way. So when I have a pole that is inside the unit circle here, for instance, I have another pole that is outside the unit circle. So therefore, it is still unstable. I have to have all the poles inside the unit circle for the system to be stable. Okay. So let's look at an application of the root locus. Suppose that for the system that we just plotted, this is the root locus. I want to find the value of the gain k that places the poles of the closed loop system at a certain location. So imagine that I want my system, this is not the unit circle, this is the root locus. I want my system such that if I were to vary the gain, I want my poles to be operating at these two dots that I plotted here. And this is continuing the example that we started. What is the value of the gain k that will result in the system having the poles at these two locations? So to find that out, we can just say that for these two poles to be on for the system to be operating at these two poles, and we're going to call them ZD and ZD star, or conjugate, we're going to have 1 plus k g of ZD equal to 0. Therefore, the magnitude of g of ZD has to equal to 1 over k. Remember, the poles, in order to be on the root locus, they have to satisfy the magnitude criteria and the phase criteria. The magnitude criteria says that 1 plus k g of ZD must equal to 0. So therefore, I can solve the value of k. K has to equal to 1 over g of ZD. And to find that out, we just have to substitute for z with ZD. So therefore, if I plug in ZD, I'm going to get ZD minus 1 multiplied by ZD minus 0.6 over ZD plus 0.8. And what this is going to equal to is ZD minus 1 multiplied by ZD minus 0.6 over ZD plus 0.8. Now, if I look at this, I can go back and look at the graph that I have above. I realize that what are these distances? What I'm calculating here is nothing other than the distances. ZD minus 1 is the distance between ZD and 1. ZD minus 0.6 is the distance between ZD and 0.6. ZD plus 0.8 is the distance between ZD and 0.8. So therefore, if I want to know the value of the gain so that I'm operating as ZD, I can just take the distances, which is L1 distances, which is going to be, I have them here probably mislabeled, L1, this is L1, L2, and this is L3. I'm going to take L1 multiplied by L2 divided by L3. So the distances to the open loop poles divided by the distance to the open loop 0. Okay. So again, if we want to graphically calculate the value of this gain, that will result in the system operating at any point, I just have to calculate this distance to L1, this distance L2, multiply them, multiply the distances to the poles, divided by the distance to the 0. Of course, another way of finding this, if I use MATLAB, I can use R root locus find. I can click on the root locus and it will give me the value of the gain for which the system will be operating or would have its poles at that location. Okay, so this is the graph generated by MATLAB using the root locus. Now this is Octave, so it's not as clear as that of using MATLAB, but nevertheless, you can see these are the two poles here, and this is the 0, and this is the root locus. Okay, I hope this helped refresh on the root locus. Please review the notes, and if you don't have the notes, let me know. I can share the notes that we had with the linear control. Again, the same rules apply for plotting the root locus of a discrete time system. Is similar to that of the continuous time system. The difference is how you interpret the location of the or the location of the poles on the root locus. Again, one obvious difference there, if the branch crosses the j omega axis to the right, becomes unstable. Here it has to cross the unit circle. So therefore there's an the location of the poles in the Z domain is different than the interpretation of the poles in the S domain. Okay, thank you everybody.